Our presenter is Péter Ridzi. Péter works at Continental Adas as head of AI data group. He and his team are responsible for providing the right data in the right time for the AI development project teams, which are working on perception function implementation. The title of his talk is Right Data at the Right Time, Fueling CNN Development with Dataset Engineering. Péter, the stage is yours.
Hello, everyone. I'm Péter Ridzi from Continental Adas, and I'm leading the data group in the AI Development Center in Budapest. And just as Peter said, my team is responsible for providing the right data at the right time for the development teams. In the following half an hour, we will touch quite some topics. First, I will start an introduction to our domain, what is an ADAS function. And then I will go into the details of dataset engineering, what is our concept, how do we handle that. And we will walk through customer project lifecycle, what kind of data challenges do we have there, how do we solve those issues through a few examples. And before the end of the talk, we will look under the hood to see what are the building blocks of our architectures to solve these problems. So Continental is sharing the dream of Vision Zero, a future without accidents on the roads. And the contribution of our business unit ADAS is to implement different driving assistant functions like adaptive cruise control, automated parking, or emergency brake assist systems. And each of every ADAS function has 3 different steps. First, the car needs to know what is the environment, what kind of static dynamic objects are there around the car, what kind of road paintings are visible, and also the traffic light, traffic signs might be interesting in case of some use cases. So basically, this is the perception part when the car senses the environment. And after that, we need to plan what should we do. What kind of trajectory should we choose, what kind of actions should be triggered, and basically we need to know what is the actual scenario we're in currently. So this is the brain of the car when the planning is happening. And finally, we need to execute this brake event or steering maneuver in the act phase. The main scope of the Budapest AI Development Center is the first part, the sense, which means detection and also environment modeling. In my talk, I would like to focus on the detection part because this is more relevant for data management right now. The final product, what Continental is providing is a hardware-software component. So in Continental, we are working on hardware development as well. And for example, for an object detection function, we implement an embedded CNN software component, which we run on this hardware with limited resources, of course, realizing the final function. So object detection means, in this case, on camera images that we get a camera image and we need to locate and classify each and every road users there. For example, pedestrians, cars, trucks, bicycles, motorbikes, and so on. And it will be integrated into other parts of the tool chain, just as I mentioned before. Such a project runs at least 1-2 years from the concept building pre-development step until the start of production. So this is the end of most of the projects when the manufacturing part is started and the hardware component is integrated into a car. So if you buy a new passenger car, let's say, there's a chance that a Conti camera is running behind your mirror there. And data management plays a key role in the detection software development. We will go into details later on. Why is it so important? So currently we are living in the age of software 2.0, and I got this concept. I heard it from Nicholas Kamczycki from NVIDIA, and it pretty well explains what is our approach if we are talking about data management, dataset engineering. So in traditional software development, there is a problem space that needs to be solved and given an engineer. And the main task of this engineer is to write a program code which covers all the different cases, scenarios, conditions in this problem space with the required output provided by the software component. And if the program is ready, it's compiled, it's executed, we also need to run some tests on data, for example. And based on the logs, the developer might need to go back and modify the code because some conditions are still missing there. So the performance improvement can be achieved through manipulating the program code, doing several iterations. It works fine for a lot of use cases, but if the problem space is really complex, then it's almost impossible. For example, if we are talking about semantic segmentation, then there's a camera image and we need to assign a semantic label to each and every pixel of this camera image, then you can imagine how difficult it is to write each and every condition. And if you would like to change anything in the requirements, then you might need to start all over again from the beginning. So we start to use some kind of machine learning techniques, let's say software 2.0, given the same developer and this much more complex problem space. And the developer starts to write a control code, some kind of brain, machine learning framework, preprocessing, post-processing steps, and also prepares a data set with examples from the real world, example inputs with output pairs. And through a machine learning training process, this developer gets the actual program code, the predictor, what can be used for new cases, and yeah, we can see how it performs. What are the qualitative, quantitative results of this test? And if the result is not sufficient, we need to go back and either modify the program code or modify the data set. So there's always a chance that if we show more examples, more input-output pairs, then the algorithm will be better and better over time. And to decide which is the best way to improve the performance is highly depending on what kind of method do you want to use. For example, deep learning, what we are using for object detection is a data-hungry activity. But as you can see, from now on, dataset is in the same role, same position as the software component. So we need to handle the dataset as code. We need to specify it. What kind of syntax, coding guidelines do we want to use? We can translate it to data format, quality, semantic descriptions. And of course, after that, we need to implement it. We need to prepare this data set, these input-output pairs, transform it to the right format, for example, which is the major part of this development step. And we can unit test it. We can test the quality and the scenario coverage, because this is crucial if we would like to in fact improve the performance. And if we are satisfied, then we need to encapsulate this data set of examples into one artifact. This is really similar to the program code that we push into the version control system. We need to store them with unique identifier we can reference later on. And we shouldn't forget the integration part, how these data sets will interact with each other. For example, we need to be sure that the training and the test data sets are not overlapping at any means. If we have some kind of overlaps there, there's information leakage, and the outputs, the KPIs are not reliable for us. So as you can see, all parts of the software development can somehow be mapped to the data management topic as well. And this is what we call dataset engineering. This is the loop that we need to do just in line, parallelly with the software development part. Let's see, what does it mean in production? So as I said, Continental is working on a customer project, working on the hardware component and parallelly on the software component as well, which we realize some kind of detection function. The project can be split into 4 phases: pre-development, base, stabilization, and fine-tuning. In the following minutes, we will walk through them. What are the characteristics, special requests of each and every phase? I would say that the pre-development is the most interesting, all of them. We don't have the customer in many cases. We don't have the final sensor, and we are not sure what is the right concept to roll out in the customer project. So we receive a lot of ad hoc requests, There are a lot of teams, several teams are working on this activity parallelly with a few developers, and they try to demonstrate the potential solutions, evaluate them, fail fast if that's the case, and the main goal here is to reach the series project phase, to have a customer, have a final requirement list, which will of course change over time, but to the point when we can start to ramp up the teams. So in this phase, we need to handle the uncertain situations. We don't have time to execute huge data acquisition or mass labeling campaigns and activities. This is a continuous task what we need to solve. They are always pre-development projects, and after a few weeks, months, we might reach the actual series project phase. I picked one example task which is really important in this case. I said that for deep learning we need the input data, which is image information and ground truth, the target what we would like to achieve, to learn in this machine learning component. So we need to specify what is the specification of this ground truth. And in this discussion, there are three players. There's the machine learning developer who needs the labeling output. So this person can bring in the requirements. We have the tool developer who will implement the tool. And we have the labeling team who will work on the manual tasks in this tool to create hundreds of thousands of labels for the given images. And in this phase, we need to decide three things. Let's start with the marker. What is the right marker what we would like to use, which is in line with the requirements of the AI developer, machine learning developer, and can be implemented in the tool. Is it pixel mask, bounding boxes, cuboids, lines, key points, whatever you can imagine? These markers should be supported in the tool itself. The second really important part is the semantics. We have the markers, but what will be marked and what's the meaning of that? What kind of classes do we have? How do we want to handle, for example, the occlusion or truncation of different objects? Should we estimate the real size or just the visible part? What do we want to do, for example, if there are pedestrians with different accessories in their hands, umbrellas, luggages, and so on? So these are really important things if you would like to use and reuse the data later on. And the whole labeling team should have the same understanding. How do you want to handle these cases? So this is the game of the AI developer and the labeling team. And last but not least, we need to provide assist functionalities, because these labelers will use it hundreds of hours. And whatever you can improve there, help them, it's necessary. So we start these iterations in this pre-development phase and try a lot of different concepts, solutions. And after several weeks, we will have this specification, this label spec, which will help us to use the data and reuse it later on in the next pre-development project. And we need to have the final decision when the series project starts. Now we have a bigger team. So the big team ramp up is started. They work on the deep learning part, and they require a lot of data. We need huge data sets, representative data sets, which covers all the different scenarios. All the relevant classes are there. We need to handle different labeling teams to understand the specification, provide the results in the right quality, and so on. And this part takes for a few months, but there are a lot of data activities. We need to scale out everything that we evaluated previously. And finally, we need a solution which is demo ready, so we can go out, start test it, and get feedbacks. The solution or the task what I picked here is the data pre-selection. How can we prepare and compose this huge data set with diverse scenarios and representative distributions? And I would like to split these two topics. So one is the representative nature of this data set, and the other one is the the diversity. So if we would like to get a representative data set, we need data from country roads, cities, highways, day, night, rain, snow, and of course data from different countries because different vehicle shapes can be there. And for the first, for this part, we have a lot of additional sensory information coming from the vehicle. So we have GPS, we have the timestamps, we have inertial measurement units, and from them we can generate, for example, country description, road type information based on the timestamp and camera settings. We know the light condition part. In fact, GPS and timestamp combination can give us what kind of weather was there on those specific segments. Oh, we store everything in a scene database because these are things that won't change over time, hopefully. The other part is that we need relevant object distribution. So we need cars, bicycles, pedestrians, and even really rare objects like motorbikes. And for that, we run pre-labeling. We pick one frame in every second from the recording, and we run a CNN on that, some public networks, for example, and have a rough estimation what is happening on the images. So here you can see an example, and the image is pretty small. However, there are false negative detections. So there are a lot of pedestrians here which are not detected, but this is not a problem. We know that there are a lot of bicycles and some cars on that. It's already a really relevant information for us. And we store this information as well for each and every recording. And we need to do that, both the static and this pre-labeling part automatically for all the incoming recordings. So we can start to pick the different frame segments to have this diverse data set. But imagine a scenario when you are driving on a highway and there is a truck in front of you, and for 30 minutes you see exactly the same thing. So there's no added value from the second frame to add to this data set. So we need to make it sparser. We can either manually select them, define some rules, pick one frame in every 10 seconds, but you might miss a lot of things. And of course, you can automate a lot here to compare the consecutive frames, and if there's a significant change, then just mark it and select to this label data set or pre-selected data set. And if we have the data, then we can continuously push out to the labeling teams, and they are giving us results in every week, every second week, so we can incorporate this data into the training pipeline. So we can have some results. We receive feedbacks. Maybe later on we can do some corrections in the distributions. But basically, this is the process what is running for weeks, months, until we reach a point when the solution, the software component, can be put into a test vehicle, so we can see in real life on a display in the car what is the detection rate. And this is the point when we say that, okay, we have a demo ready application, but now we have a lot of algorithmic issues. We need to stabilize this software. And we receive a lot of issue videos, examples that there are false positives here, they are missing detections there, and so on. And we need to handle these issues. We need to fill in the gaps with data, because as I said, one of the sources of performance improvement is data. So we need to grab this chance and start to work on that. And we need to synchronize with the other project streams, the software development part, because we need to give new data in each and every iteration. And basically, this is what's running for months, even longer than the base part. We might have a lot of algorithmic problems, and we need to expect the unexpected situation. So we need to prepare the whole data pipeline to receive and react to these cases. Here's one example. I think it's in Japan. A street, rain, and let's say that the issue is that we cannot detect these ladies with umbrellas on the left side of the image. And this is a task. the AI developer starts to investigate and analyze this issue. What might be the root cause? Maybe it's because these people are on the left side of the image, maybe because they are holding an umbrella, maybe because it's raining and basically everything is gray on this image, or is it because there's some environment here, for example, this crossing, which causes the problem? And they start to look into the labeled, unlabeled data pool and try to reproduce this problem or new data sets as well, new input data as well. In several cases, we need to do extra enrichment. For example, look for very special occlusion where when two cars are occluding each other, for example, or something like that. And this whole process should be self-service. So there is no chance to define the problem to another team who will investigate this issue. Many cases, the AI developers should do it on their own. And if we have this root cause, of course, we need to select a lot of similar scenarios, prepare a data set, hand it out to the labeling teams. If we receive back, retrain the model and see if we manage to fix it or not. And the whole process should be really fast. This is the biggest challenge here. Let's say we have a bi-weekly sprint. We need to handle the whole loop, execute the whole loop in 2 weeks. Labeling takes at least 1 week, retraining 2 days. So we have, let's say, 2 days to do this kind of analysis and data selection. So we need to prepare everything on our side, what is possible to make it faster. And after some time, several months, we get less and less issue reported where we can really find a root cause. Maybe the root cause is inside the CNN architecture or something like that. So you cannot really define and describe it in human language what is the problem, but still there are flickering boxes. So we need to improve the algorithm still. We need to do it fast, and this fine-tuning part can run for several months, maybe years, even after the production. We need to handle that. And one solution what we can do is active learning. This is the ultimate solution of everyone working on similar topics. We need to remove the human from the loop. So let's say in this example, we have this night image, and the issue is that some detections are disappearing for a few milliseconds, then we see them again, and it's not good. We cannot fix it at any parts of the tool chain, not even on tracking or environment modeling. It causes a lot of issues, so we need to solve it on the detection part. But we don't know. There are a lot of similar images one after the other, so just seeing them, browsing, querying, we cannot really identify what is the problem. So we use the current, what we can do is that we use the current model, what is running in the product, which observe this strange behavior. And using that model, we assign relevance score to the unlabeled data. Here you can see some examples. Relevance score can be the uncertainty of the network, for example. If you would like to define the confidence of a detection from a scale 1 to 100, then we are not interested in the 99 or the 2, but we are interested in the 49, 51 or something like that, when the network cannot really decide if it's a detection or not. And we need to incorporate these aspects into the relevance score, so we have an overview of the unlabeled data, what might be relevant for us. We store it, and after that, we can use these scores to select the top 1,000, 10,000 frames from this pool, hand it out to labeling. Because let's say 10,000 frames is the maximum what they can handle in 1 week. And after we have the model, we retrain them. There we can refresh the model itself, so we can get different relevance scores. Because if we fix some problems, then maybe those frames got a a smaller relevance score, so we can have the refreshed attribute there what can be used. And here, as you could see, we eliminated the human. We need, of course, update the model. We need to do the manual labeling or the correction of the labeling. However, for data selection, we cannot do that. And this is something that we can do in this fine-tuning phase, but before that, there are more effective ways to fill in the algorithmic gaps. So there's no need to apply it earlier. And as we go further into the project, we have more and more available data. So the data acquisition is going on. We have more and more recordings. However, the relevance of new data just decreases significantly at the beginning. However, even after several months, we still have some edge cases what we can solve with this fine-tuning approach. So there is continuous data need after several months as well. And this is what we call the long tail of scenario distribution. And more than half of the data, the final data set, what is used for development, is being is coming from these phases, the stabilization and the fine tuning. So you need to fine tune your processes as well, automate as much as possible to be able to handle it. So these are the project life cycles: pre-development, the huge uncertainty; the base development, when we need to provide huge data set in a few months, representative distribution. In stabilization, we try to analyze the root causes, fill those gaps with data in a few months period. In the fine-tuning, we have a target to continuous improvement. Each and every step has their characteristics, and as you could see, there are a bunch of data tasks in each phase. Let's see what kind of tools, what is the architecture what we can use to solve these problems. And there are three principles what we followed when we started working on the different development tasks. One is that we need an integrated solution. So there's no way that we do anything manually loading data from here to there. So if we can integrate something, let's do that as well. Automate everything what is possible. If you got a question today, you manage to solve it, you might have a more complex one tomorrow. So if something is solved, then you need to incorporate it into the process. And of course, we need to democratize the data management. So everyone should handle their own data, query it, check what is missing. In the center of our architecture, there's a metadata storage. Here we store all the available descriptive informations, automatic labels, manual labels, everything available for the recordings, images, videos, what we have. And we built it based on a data lake, data warehouse architecture. So we have a stage layer where there's the extracted signal information, for example, the GPS. We have a core where we run the different enrichments, country, road type in a structured way. So we can always query data from here if we need that. And search is optimized for query for the users to do so. We need an artifact store. As I mentioned at the beginning, it's crucial to have one place where you store the version control data sets. And for that, we have an artifact store, which is MongoDB for fast random data access. And we have a high performance storage which stores all the image information, the input data for the training. And the GPU cluster, DGX GPU cluster is integrated into these two systems layers, so they can pull in the data during the deep learning training. And yeah, question is, what will generate the data? How will we receive it? We have a processing framework. This is running on Kubernetes, and there are GPU and CPU parts as well. In CPU, we can load these ETL jobs, not just load the stage, but load the core, search, and so on. In a provisioned way, we can track what was the method which generated which data and so on. And also in the CPU part, we do the preprocessing. So we need to generate these special image formats for deep learning. And we have a GPU part as well, which is equally important. Here we run the inference related parts, for example, pre-labeling or score calculation, and so on. And we need to execute the same processes for each and every recording what comes in through the data acquisition campaigns. And finally, we work on a web application as well, which is the single entry point for the majority of our users. So they can log in, they can browse the data, they can browse the metadata, they can create data sets, and using the unique identifier, they can reference it in the deep learning training network. We see that this is really a huge help for them and for us, of course, because they can handle a lot of activities on their own, and they really appreciate it because, yeah, this kind of data management should be democratized in the organization and the groups as well. So basically, these are the main building blocks, roughly as an overview. We have a breakout session after this talk where my colleague Csongor Santo will give you a demonstration of this web application as well. We can also dive into technical topics if you have. Yeah, feel free to join, come for discussion. And we are still building up the team. So we are always looking for enthusiastic developers who would like to contribute in this dream to reach the Vision Zero, a future without accidents. Yeah, thanks a lot.
All right, thank you very much, Peter, for this very exciting and interesting talk. There are a couple of questions. Hopefully we'll have time for all of them. So I'm just going to jump right into it. The first one goes like this. Again, it's two questions. Sometimes one question is two. How do you acquire sample data like images, and how is privacy handled in the case of such images?
Yes, so we collect data using our own fleet. Continental fleet. So we have several vehicles running on different continents collecting the data. There are internal processes. How do we screen the data, blur images and number plates? There are compliance requirements for internal usage, and there are much stricter compliances if we would like to hand it out. We are working with external labeling teams as well, where it is mandatory. So if we have these pre-selected data sets, we run some anonymization processes on top of that. It is basically a CNN which detects the faces and number plates, and those parts are blurred out. Yeah. This is a really simple process. What we can do, of course, there might be problems with that. For example, if some relevant parts of the frame is blurred out, then the labeler cannot really decide where is the edge of the object. But this is really efficient, I would say.
All right, thank you very much. And I'm going to skip one question because this one relates to this one, and then I'm going to get back to that question.
Okay.
But the question that relates to the previous one is, do you use simulation in order to generate more data, or you collect data only from the real world?
A really good question. Thanks a lot. I was expecting that at some point. Yes, we are using simulated data. However, for detection function, simulated data is not that efficient, because the real question is, what are the different reflections on the vehicles, for example, what kind of shapes are there in the real world. And in fact, the biggest problem is not those cases. Yeah, so the biggest problem is not caused by those cases that we can describe, for example, in a simulation environment, but the unexpected scenarios. So this is the main reason why real-world data through data acquisition campaigns is more efficient than simulated data. Later phases of the development, environment modeling, or even the driving function part, yeah, this is crucial. So there are a lot of simulation topics as well here.
All right, thank you very much. And finally, the last question. Would you consider to replace the CNN architecture to transformer architecture? Tesla's autonomous driving has some pretty promising results about it. It is way more computationally efficient.
Yes, this is something which is not my expert field, so I'm not the right person to answer it. I know that we are working on a lot of different methods like transfer learning, unsupervised learning techniques, and other data efficient training methods as well. Yeah, so I'm not the one who can answer that. Sorry for that.
All right. Thank you very much. I'm very happy that we had time for all the questions. Thank you, dear viewers, for asking them. And thank you, Peter, for these very insightful answers and also for your talk.